Let's quickly revise 9th Standard ICSE Physics Chapter 1 Measurements and Experimentation, the Vernier Scale. Now the usual ruler, the meter rule, is useful in measuring up to an accuracy of 0.1 centimeter or 1 millimeter. That is its least count. But what if we want an accuracy up to 2 decimal places? Then we use the vernier calipers. In the vernier calipers, as you can see, we have the outside jaws or the inside jaws, which can be useful in measuring the diameter of substances or even the thickness or the length of substances. We have this strip at the end, which is like a tail, which is useful in measuring the depth of substances, like a glass bottle. We have the main scale with the least count of 0.1 centimeter, and we have the vernier scale, which is movable on the main scale. The use of vernier calipers is to measure the length of a rod, diameter of a sphere, etc. Formula used in measuring it is the total reading is equal to the main scale reading plus the vernier scale reading. The main scale reading is a reading on the main scale, which will come up to 1 millimeter accuracy. Let's say the length of a rod was 5.6 centimeter. But I want accuracy up to 2 decimals. So for that, we look at the vernier scale. Now the vernier scale reading formula is the least count multiplied by the coinciding division of the vernier scale. The least count of vernier scale is usually 0.01 centimeter or 0.1 millimeter. But how is this calculated? Well, the formula for least count of a vernier scale is 1 main scale division upon number of vernier scale divisions. In this diagram, for example, 1 main scale is 0.1 centimeter. So 0.1 centimeter upon number of vernier scale divisions. So here in the vernier scale, which is a red rectangle, I see 10 divisions. So upon 10. So the least count here is 0.01 centimeter. If you want to decrease the least count, that is increase the accuracy of the instrument, then there are 2 ways. Either you decrease 1 main scale division on the main scale, or you increase the number of vernier scale divisions on the vernier scale. Lower the least count, more accurate is the instrument. So 5.6 centimeter plus least count is 0.01 into coinciding division. So in this diagram, look at which division is coinciding between the vernier scale and the main scale. The 4th division is coinciding. So 4. The final answer comes up to be 5.64 centimeter. So we get the answer accurate up till the 2nd decimal. It's possible that due to wear and tear, there might be a 0 error in the vernier scale, which means that when the jaws are together, even before starting the measurement, if the 0 of the vernier scale and the 0 of the main scale are not coinciding, then that is called a 0 error, which means that the final answer is not accurate, which means that in the end we may have to add or subtract the 0 error to get the accurate answer. Now, there are 2 types of 0 errors. The positive 0 error happens when the 0 of the vernier scale is initially to the right of the 0 of the main scale, and negative 0 error happens when the 0 of the vernier scale is to the left of the 0 of the main scale initially. Now, what if I want measurement up till 3 decimals or 4 decimals? I need an instrument which is even more accurate. That means something which has an even smaller least count, and that is screw gauge. And if you want accuracy up till 4 decimal places, that is called a micrometer screw gauge, which looks like this. Now in a micrometer screw gauge, we see how the spindle, that is B, can be rotated with the help of the ratchet such that it can move forward or backward. Initially the spindle is touching the stud, but if we want to measure the thickness of a paper or a wire, we put it between A and B, that is the spindle and the stud, and we rotate the ratchet such that the spindle presses against the object tightly, but not too tight. On the sleeve here, we have the main scale, and the line is called the baseline. And on this hollow cylinder called thimble, we have the circular scale, which will have circular scale divisions, usually from 0 to 100. The logic behind it is the same. The formula is total reading or final reading is equal to the main scale reading plus the circular scale reading. Here, the circular scale reading is again least count multiplied by coinciding division. Main scale reading again will give us the answer up to 1 decimal accuracy. Let's say 5.6 centimeter. Now least count of a screw gauge has a formula: pitch upon number of circular scale divisions. But what is pitch? Now, pitch of a screw gauge is the linear distance moved by its screw on the main scale when the circular scale is given one complete rotation. The pitch is 0.1 centimeter. And if you take the number of circular scale divisions as 100, then the least count comes up to 0.001 centimeter. Here, I can see 1 millimeter, 2 millimeters, but I can't see the 3 millimeter mark. So the main scale reading is 2 millimeters or 0.2 centimeter. So now, on further calculation, I get the answer as 0.205 centimeter. So I got accuracy up till 3 decimal places. If we could decrease the pitch further and increase the circular scale division, we might get a least count of 0.0001 centimeter, which will be a micrometer screw gauge, giving us the answer up till an accuracy of 4 decimal places. Now, even here, we can have zero error. So initially, when the stud and the spindle are touching each other, even before the measurement begins, at that time, if you see the zero of the circular scale division below the baseline, it is called positive zero error. If you see the zero of the circular scale division above the baseline, initially, we call it a negative zero error. We may also have something called a backlash error. This happens due to wear and tear. So while we are rotating the screw, and if we suddenly change the direction of rotation, even though we are rotating the screw, it may not move, due to which we may get an error in its reading. So the solution to that is, we should never change the direction of rotation suddenly. Suppose we are rotating it clockwise and we want to rotate it anti-clockwise. Then continue rotating it clockwise, slow down, come to a stop, pause, and then start rotating it anti-clockwise. This will remove the backlash error.
Section B, Measurement of Length, Chapter 1, Physics. Least count of an instrument is the smallest measurement that can be taken accurately with it. For example, the least count of a wall clock is 1 second. Cancel all of these. Now here, what is the main scale reading? It's 1.2 centimeter. But the actual reading should be between 1.2 to 1.3 centimeter. So to get the accuracy up till the second decimal, we use the Vernier scale. Here, we need to understand what is the coinciding division. I can see that it is 1, 2, 3. The fourth division is coinciding between the Vernier scale and the main scale. This will be helpful for us to find the Vernier scale division, and then the final reading will be accurate up to 2 decimal places. So the formula is total reading is equal to main scale reading plus Vernier reading. In the diagram, the main scale reading was 1.2 centimeter, as I said. And the Vernier reading is nothing but the coinciding division, which was 4, into the least count. The least count of that Vernier scale was 0.01 centimeter, since it gave us accuracy up to 2 decimal places. So adding that, we get the final result as 1.24 centimeters. This is the logic behind using Vernier calipers, which is also called slide calipers. It is used to measure the length of a rod, the internal and external diameters of a hollow cylinder, etc. The description is totally cancelled, although you need to know the parts of the Vernier scale and their uses. That's important. The outer jaws and the inner jaws are used to measure the diameter, the external and the internal diameters of spheres, pipes, etc. The strip is used to measure the depth of a beaker or a bottle. This is the main scale. It's shown broken out here just to jump from 4 to 10 centimeter directly. This is the Vernier scale, which would measure length correct up to 0.1 millimeter or 0.01 centimeter. Now the least count of Vernier calipers, also called Vernier constant, is defined as it is equal to the difference between the values of one main scale division and one Vernier scale division. But the formula is different from the definition. It is the value of 1 MSD upon total number of Vernier scale divisions. Now, as per definition, the main scale reading is 0.1 centimeter. Each reading on a Vernier scale is 0.09 centimeters. So after subtraction, we do get the least count as 0.01 centimeter, which is the same value we would get by using this formula. There are two ways to decrease the least count, that is increase the accuracy of a vernier caliper, either increase the denominator here or decrease the numerator here. But often when we start using a vernier calipers, the zero of the main scale and the vernier scale may not coincide, which means that there is a zero error. So to compensate for that, we have to add or subtract that zero error in the final answer. Now initially, when the jaws are touching each other, if the zero of the vernier scale is to the right of the zero of the main scale, we say there is a positive zero error. So in the end, we should subtract that value. On the other hand, if the zero on the vernier scale is to the left of the zero of the main scale, it is called a negative zero error, and we'll have to add that error in the end. How that zero error is calculated is not in syllabus, but the correct reading is the observed reading minus the zero error. A positive zero error will be subtracted, but a negative zero error will be added in the end. This experiment is cancelled. Now let's look at this example. Imagine there is no zero error. Now what is the main scale reading here? Well, I see that the red line is till here. That is, it's between 5.3 and 5.4 centimeters. So we say the main scale is 5.3 centimeters. And now for the vernier reading, first find the coinciding division. 1, 2, 3, 4, 5, 6. I see the sixth division is coinciding. So the coinciding division is 6 multiplied by the least count, which is 0.01 centimeter. So we get the vernier scale reading. And the observed reading is the main scale reading plus vernier scale reading. 5.36 centimeter is the final answer. So that's how we get answers accurate up to 2 decimal places. But what if you want an answer up to 3 decimal places? Then we use a screw gauge. So all of this is cancelled. You just have to know that screw gauge works on the principle of a screw, and it is used to measure the diameter of a wire or the thickness of a paper. You can even get accuracy up to 4 decimal places if you use a micrometer screw gauge. It looks somewhat like this. You keep the paper between the stud and this spindle. Using the ratchet, you can rotate the screw so that it will slowly head towards the stud, and the paper will be stuck between the stud and the spindle, tightly pressed together. This is the main scale reading on the sleeve, and this is a circular scale reading. So you can see 0, 5, 10, 15, all the way around. It may go up till 50 or 100 and come back to 0. The description need not be studied, but the uses of each part should be studied. Remember, the circular scale helps us to read the length correct up to 0.01 millimeter or 0.001 centimeter. Although the least count of the main scale is still the same, 1 millimeter or 0.1 centimeter. Now we need to understand a couple of definitions here. First of all, pitch. Pitch of a screw gauge is the linear distance moved by its screw on the main scale when the circular scale is given one complete rotation. So imagine this is a screw. This is the starting point. If I rotate it one complete time, how much has it gone ahead on the main scale? That is called the pitch, which is usually 0.1 centimeter. Now the least count of a screw gauge is the linear distance moved by its screw along the main scale when the circular scale is rotated by just one division on it. So for pitch, I said you have to rotate it by one complete rotation. But for least count, we should rotate it just a bit, just equal to one division on the circular scale. So by how much will it move ahead? That is called the least count of a screw. So the least count has a formula, the pitch of the screw gauge upon the total number of divisions on its circular scale, which is usually 100. So if the pitch of the screw, that is the distance traveled after one complete rotation, if that is 0.1 centimeter and the total number of divisions is 100, then the least count becomes 0.001 centimeter. So now you see how we can get an accuracy up to 3 decimal places. But how to make it even more accurate? That is how to decrease the least count. Remember, lower the least count, more accurate the instrument is. So same logic, either you increase the denominator, that is number of divisions on its circular scale, or you decrease the pitch of the screw gauge, that is decrease the denominator. Now even here, we may have a zero error. That is, in the very beginning, when the stud and the spindle are touching each other, the zero of the circular scale division may not coincide with the zero of the main scale division. So if the zero of the circular scale is below, we call it a positive zero error, which has to be subtracted in the end. But if the zero is above, we call it a negative zero error. So we just have to remember the definition and the diagram. The calculation part is not to be studied. So the final reading will obviously be the observed reading minus the zero error, just like in the previous case. All these experiments are cancelled. let's do one sum here. First of all, what is the main scale reading? 0, 0.1, 0.2, 0.2 centimeters. And what is the coinciding division here? I see 56 is coinciding with the baseline, with the main scale. So 56 into the least count. And the least count for this sum is given in the question as 0.001 centimeter, which is usually the case. So the observed reading is 0.2 plus 0.056 centimeter, which is 0.256 centimeter. And here we are assuming that there is no zero error. Finally, we have something called the backlash error. Sometimes, due to wear and tear of the thread screw, even when you rotate the ratchet, you see that the screw is not moving forward. This will give us an inaccurate answer. So what we should do is, whenever you want to change direction of rotation, don't immediately do it. You slowly come to a stop, keep moving forward, pause for some time, and then you rotate it back if you want the screw to come back. This way, there would be no error. Remember this note as well. Notice that smaller the least count, more accurate it is. So which of these has the lowest least count? Screw gauge. And which is the most accurate? Screw gauge.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.